Lesson 2, the equilibrium constant. The equilibrium constant expression. Chemists have found that there's a mathematical relationship between the concentration of the reactants and products once equilibrium has been reached. That is independent of the initial concentration of the participants. For any general reaction, so we just write that simple general reaction, A of A plus B of B is in a reaction to form C, that should be C of C plus D of D. An equilibrium constant expression can be written as such. Concentration of the products to the power of the number that was in front of the element divided by the concentration of the reactants divided by, or to the power of the number that was in front of your element. So remember, it's always going to be products over reactants. This mathematical relationship exists for all equilibrium systems and produces a constant ratio called the equilibrium constant Keq. This equation is sometimes called the mass action expression, and the product of the reactants, C and D, are placed in the numerator, so it's the top, and the concentrations are raised to the power of the coefficient of the balanced equation. The reactants, A and B, are placed in the denominator, with the concentrations being raised to the power of their coefficient. And that will make sense when we look at some more. Remember how to set up this equation, because it's another equation that we're going to be using quite a bit. So here's an example. For the reaction between hydrogen and iodine gas to produce hydrogen iodide, we've looked at before. The equilibrium expression will be written as such. So we have H2 plus I2 gives us 2HI. So we have the concentration of the products on the top raised to the coefficient, and the coefficient here is 2. Then we have the concentrations of the reactants raised to their coefficients, but their coefficients are 1, so it doesn't count. And then we multiply those together. We're given some concentrations that we want to fill in and use that to figure out what our Keq is. So let's write down our formula here again. Concentration of HI, and that's squared, remember, divided by the concentration of H2 times the concentration of HI2. So the numbers we were given before, 0.156, and that's squared, divided by 0.22 times 0.22. So I put that in my calculator, and I end up with 50.3. The K-equilibrium answer does not have a unit, so you don't have to worry about figuring out what that is. If you're unsure of how this goes in your calculator, I can show you in class tomorrow. It's fairly easy, you just have to follow some steps. Like I was saying before, the value of K-equilibrium has no units. It's a constant for any particular reaction, and its value does not change unless the temperature of the system has changed. It does not depend on the initial concentrations used to reach the point of the reaction at equilibrium. For example, the following data were obtained for equilibrium concentrations of H2, HI, and I2, and the values of K-equilibrium were calculated for each trial. Aside from accounting for slight experimental variation between trials, the K-equilibrium is the same despite differences of equilibrium concentrations for the individual participants. So if you've noticed, This is the one that we looked at right here. We get about 50.3, and they change the concentration of the initial HI, or they changed the concentrations, and all the way through we ended up getting about the same concentrations, or same K equilibriums. Some important points. There's one other important point to make at this time. K equilibrium relates the concentration of products to reactants at equilibrium. For aqueous solutions, so those are solutions that are dissolved in water, concentration is often measured in moles per liter. For gases, concentration is often measured as a particular pressure. For concentrations of both aqueous solutions and gas change during the process of reaction, for the reactants involved in a solid or a liquid, while the amounts of the solid and liquid will change during the reaction, their concentrations, much like their densities, will not change during the reaction. Instead, their values remain constant because they are constant. Their values are not included in equilibrium constant expressions. So that's really important to remember. If you ever come across a solid or a liquid, their concentrations never change, which means their concentrations are not included in the K equilibrium expression. Here's an example of that. Consider the reaction showing the formation of a solid calcium carbonate from solid calcium oxide and carbon dioxide gas. So the equilibrium constant for this reaction before its modification. We have the products over the reactants. Products over reactants. Okay, but we remove the those participants which are either in a solid or a liquid, which is the calcium oxide and the calcium carbonate. So that means that goes away and that goes away. So because there's nothing on the top, we just have one, and the only other participant in the reaction is the carbon dioxide. So the K equilibrium is 1 over the concentration of the carbon dioxide. So what does K equilibrium mean? What does it mean? What can it tell us about a reaction? If the KEQ is very large, the concentration of the products is much greater than the concentration of the reactants. The reaction essentially goes to completion, or most, if not all, of the reactants are used up to form products. If K equilibrium is very small, the concentration of the reactants is much greater than the concentration of the products. The reaction does not occur to any great extent. Most of the reactants remain unchanged, and there are few products produced. If K equilibrium is not very large or not very small, but very close to 1, then roughly equal amounts of reactants and products are present at equilibrium. So some examples of that. The decomposition of ozone, so O3. So 2O3 gives us 3 oxygen gas. Okay, the K equilibrium is 2 times 10 to the power of 57. So that would be 2 followed by 57 zeros. This is a very large number that indicates that mostly oxygen gas is present at equilibrium state and very little ozone gas. So next example, the production of nitrogen monoxide. So nitrogen gas and oxygen gas gives us 2 moles of nitrogen oxide. And the K equilibrium is 1.0 times 10 to the negative 25. So that means following the decimal, there's 24 zeros and then the 1. It's a very little number, which means there's very little nitrogen oxide produced in this reaction. Nitrogen and oxygen do not react readily to produce nitrogen monoxide, which is good for us because then we can breathe. Reaction of carbon monoxide and water. So CO plus H2O gives us carbon dioxide plus hydrogen gas. So the K equilibrium is about 5, which is kind of close to 1 if you're looking at the other numbers. The concentration of the reactants are very close to the concentration of the products in this equilibrium. Alright, so that's your lesson for the day, and we will see you tomorrow to do some assignments on finding